Alrighty, so welcome Verde Valley to the Asteroid Bennu Science Cafe. I'm Jeff Anderson, the Outreach Coordinator for the Verde Valley Stream Council. Our council works to bring informal STEM learning opportunities to our communities, and that's what this Science Cafe is about. So by informal opportunities, we mean STEM education outside of typical school systems, and like high school or elementary, middle school, or even college. And the other important thing is it crosses all age boundaries. So that from youth to retirees, we're really trying to focus on providing just some cool STEM opportunities for people to learn about things. I did want to give a shout out to a group of youngsters watching today. The summer camp explorers at the Science Vortex of the Verde Valley are tuned in, and thanks for watching with us, kids. As you may know, the Science Vortex is one of our partners today for the cafe. It's a new organization in the Verde Valley, and it offers STEM summer camps, after-school programs, and soon science exhibits for locals and out-of-town visitors. You can find out more about the Science Vortex by visiting their website, sciencevortex.org, and I'll include that URL later in the Zoom chat in QA. So let's get ready for our presentation on the OSIRIS-REx NASA mission by giving some background on our guest speaker. Dolores Hill is a senior research specialist for the Lunar and Planetary Laboratory at the University of Arizona. She's a member of NASA's OSIRIS-REx asteroid sample return mission, and she serves on the communication and public engagement team. She's the OSIRIS-REx ambassador lead, as well as a co-lead of its Target Asteroid Citizen Science Program. This program was honored by the White House Champion of Change for Citizen Science in 2013, and that's where US citizens can get involved in science initiatives. So since 1981, Dolores has analyzed a wide range of meteorites at the University of Arizona's Lunar and Planetary Laboratory and provided technical support to space missions in LPL laboratories. In addition to her work analyzing meteorites, she has a lifelong interest in amateur astronomy. She's a longtime member of the Tucson Amateur Astronomy Association, co-founded the Sunset Astronomical Society in Midland, Michigan, and was a member of the Warren Astronomical Society in the Detroit area. Near-Earth asteroid 164215, Dolores Hill, is named after her, which is really cool. She looks forward to seeing samples of the near-Earth asteroid Bennu when it returns in 2023. So let's welcome Dolores Hill. Hi, Dolores.
Hi there. Good afternoon. It's great to be here.
Yeah, it's really cool that you've got an asteroid named after you. That was surprising.
It is very cool. It is. Unfortunately, I'll never see it in my telescope, but that's okay.
That's fine. So before I hand this off to Dolores and just let her take over, I wanted to do a quick poll to see how many viewers had a chance to watch the YouTube video we sent in email. And the title of that video was "To Bennu and Back, an OSIRIS-REx mission overview." It was about 7 minutes long and covered the mission activities through about, I think, January 2019, which is over a year and a half ago. So Dolores is going to update us on really what's been happening since. So let me pop this poll up real quick and see how many people actually had a chance to watch that video. All right, so we get some results coming in, and about so we've only got about half of the people have watched, a little over half. And so I'm going to, I think I'm going to play it again, if that's okay. It's only about 7 minutes long, and it gives a good background for people who've missed that. So let me share my screen. And Dolores, if there's anything that you want to say about it during or after, that's great. So
okay.
So I'm going to put my screen in full mode, and hopefully this plays for us.
OSIRIS-REx is a NASA mission to explore near-Earth asteroid Bennu, a remnant from the dawn of the solar system, and to return a sample of Bennu to Earth. On September 8, 2016, OSIRIS-REx began its journey to Bennu from Cape Canaveral, Florida, aboard an Atlas V rocket. It lifted off shortly before sunset, climbing eastward over the Atlantic Ocean to traverse the night side of Earth. 1 hour later, OSIRIS-REx separated from its Centaur upper stage rocket and drifted into space. It deployed its solar arrays to catch the rising sun and made a final pass over Australia before embarking on its outbound cruise to Bennu. After a year in orbit around the sun, OSIRIS-REx briefly returned to Earth in September 2017 for a gravity assist. The spacecraft passed within 18,000 kilometers of Antarctica and turned its instrument deck toward home to capture images and spectra of the Earth and the Moon. The gravity assist bent the trajectory of OSIRIS-REx by 6 degrees, matching the orbital tilt of Bennu and sending the spacecraft on a path to catch its target. In August 2018, OSIRIS-REx began its approach phase. Its long-range camera captured the first visible light images of Bennu as a single pixel moving across a field of stars. Over the following months, Bennu grew from a pixel into a world, with OSIRIS-REx revealing its shape, rotation, and color for the first time. Now, after chasing its target for over 2 years, OSIRIS-REx is arriving at Asteroid Bennu. On December 3rd, it will fire its thrusters to match Bennu's velocity and begin its preliminary survey. OSIRIS-REx will pass high above the equator and the poles, measuring Bennu's position and mass, and refining its size, shape, and spin. On New Year's Eve, OSIRIS-REx will venture close enough to Bennu to be captured into orbit by its minuscule gravity, making it the smallest world ever to be orbited by a spacecraft. In early 2019, OSIRIS-REx will break orbit to conduct a detailed survey of Bennu. First, it will carry out a mapping campaign called the Baseball Diamond. By observing Bennu at different latitudes and times of day, OSIRIS-REx will capture stereo images and identify large rocks on the surface that could pose a hazard later in the mission. In its second mapping campaign, OSIRIS-REx will observe Bennu from 7 different stations around its equator. At each station, it will take measurements from pole to pole using its mapping camera, laser altimeter, and 2 spectrometers. The combined data will provide a detailed look at Bennu's geologic features and its composition. This will improve landmark-based navigation and enable mission planners to begin looking for places to collect a sample. Following the detailed survey, OSIRIS-REx will once again enter orbit. At a radius of only 1 kilometer, Orbital B will serve as the mission's safe home orbit until sample collection. During this phase, OSIRIS-REx will globally map Bennu. It will fly in a polar orbit as the asteroid rotates beneath, enabling full coverage of the surface. Orbital B's precession, or wobble, will also be used to measure Bennu's gravity field, along with the non-gravitational forces that are slowly altering Bennu's trajectory. In mid-2019, OSIRIS-REx will begin its reconnaissance phase. It will break orbit and fly over 4 candidate sample sites at 225 meters, taking high-resolution images. Flying at such close proximity will reveal large pebbles that could pose a hazard during sample collection. Mission planners will use this information to select the 2 best sites for additional inspection. At a range of 525 meters, OSIRIS-REx will fly over the 2 final candidate sites, spectrally mapping the surface to reveal its chemical composition. This information will help mission planners determine the most valuable site for collecting the sample. Once the final site has been selected, OSIRIS-REx will begin its rehearsal phase. First, it will practice autonomous flight to a predetermined checkpoint, where it will start its descent during sample collection. Next, OSIRIS-REx will practice flying to the match point. The spacecraft will lower to within 30 meters of the surface to match Bennu's speed and rotation, a necessity for safely touching the asteroid. Finally, in mid-2020, OSIRIS-REx will be ready to collect a sample of Bennu. Before it descends to the surface, the spacecraft will deploy its touch-and-go sample acquisition mechanism, or TAG-SAM, a new technology invented for the mission. When it reaches the checkpoint, OSIRIS-REx will begin its final descent. It will pull back its solar arrays for safety and approach the surface at centimeters per second, the walking pace of an insect. If the TAG-SAM touches down, it will blow high-pressure nitrogen gas into the soil, stirring up loose material. A filter within the sample head will trap rocks and dirt while allowing the gas to escape to space. Once the sample is collected, OSIRIS-REx will fire its thrusters and back away from Bennu, retreating to a safe distance with its precious cargo. Following collection, OSIRIS-REx will verify the status of the sample using a camera called SAMCAM. This visual inspection will reveal whether any large debris is still attached to the sample head, which could pose a hazard during stowage. Next, OSIRIS-REx will verify the mass of the sample. It will fully extend its TAGSAM arm and perform a spin maneuver, measuring the change in inertia to determine the sample's mass. If at least 60 grams have been collected and the sample head is clear of hazardous debris, mission planners will command the spacecraft to stow the sample. STOWCAM will watch closely as the sample head enters the return capsule and is secured in place. OSIRIS-REx will then detach the TAGSAM arm from the head, seal the sample return capsule, and prepare for its journey back to Earth. After departing from Bennu in early 2021, OSIRIS-REx will return to Earth in late 2023. 4 hours prior to arrival, the spacecraft will release the sample return capsule, then deflect away from Earth to its final orbit as its piece of Bennu comes home. The capsule will enter the atmosphere over the night side of Earth, streaking towards the central California coastline at over 12 kilometers per second. West of the Great Salt Lake, at an altitude of approximately 33 kilometers, the capsule will initiate its parachute sequence, stabilizing and slowing its descent. Upon landing in the Utah desert, the sample will be recovered, carefully removed from the capsule, and taken to the OSIRIS-REx Curation Facility at NASA's Johnson Space Center in Houston, Texas. This pristine material from the early solar system will be studied for decades to come, providing clues to the formation of the planets, to the evolution of Earth, and to the ingredients that were present at the origins of life.
So thanks everyone for taking time to watch that video. I actually have a question maybe already that was prompted by that, Dolores.
Okay.
And that is Bennu in the asteroid belt, or is it in a completely separate orbit?
It's called a near-Earth asteroid, so it used to be in the main asteroid belt. Its orbit is now entirely within the orbit of Mars, and I'll show you a diagram of that in my talk.
Okay, great. So let me just a few other things here before I hand this out over to you. I'm going to close my video and audio feeds, so that way Dolores has complete control of this. But I'm going to be monitoring the Zoom question and answer option for any questions from our viewers, and I'll may pop back in time to time to ask Dolores your questions. Alrighty, Dolores. So I'm checking out here, and take it away.
Okay, thank you. We'll share my screen here. There we go. All right. Well, greetings from the OSIRIS-REx mission. That video was actually a fantastic summary, and you'll see some of the videos and pictures in my presentation as well. This NASA mission is a partnership between the University of Arizona, Goddard Space Flight Center, and Lockheed Martin, as well as many other institutions. Soon, our spacecraft will collect a sample of near-Earth asteroid Bennu and return it to Earth in the year 2023. If successful, this will be our country's largest sample return since the Apollo missions brought back moon rocks. Today, I'll discuss the mission's interesting name, how the asteroid got its name, how we're going to collect a sample without landing. That is the important distinction here. We are only contacting the surface for 5 seconds. This is never before tried technology, and so we're very excited to be the first to attempt it. I'll tell you what we're going to learn, what we've learned so far, and the current mission status. And we have some upcoming milestones. All right. So the mission timeline is this. We were selected in 2011. Here it is, 2020. Is that pretty amazing? Our spacecraft was launched in 2016 from Cape Canaveral, Florida. And we spent about 2 years getting to our asteroid, Bennu. You saw the orbits of Bennu, the spacecraft, Earth, and we couldn't go just directly from Earth to Bennu. We had to orbit the sun along with Bennu and catch up to it and get to just the right orientation. So it took us 2 years to get there. We've been there for about 2 years, studying it, learning a lot about it in order to select our best site. We are going to collect our sample in October, is our first sample opportunity. Our match point test, again, that you saw in the earlier video, will occur August 11th. And you can tune in to Twitter to actually follow along live with that occasion. So I didn't want to leave my presentation without showing you a picture of the real spacecraft. So over on the left is the spacecraft as it was being assembled at Lockheed Martin. And on the right, of course, is the beautiful launch. And all of the NASA veterans who were there proclaimed this the smoothest launch they had ever seen. So we were pretty excited about that. So why would we want to go to an asteroid to learn about the solar system? Well, because asteroids were the first solids to form in the solar system, and they're like snapshots in time. They reveal the formation and history of the solar system. Some asteroids, like the one we've chosen, have not changed very much since they were first formed. Others have been radically transformed by collisions and melting. Asteroids are basically big rocky bodies that orbit the sun. Meteoroids are smaller objects that are only 3 feet or less. Meteorites, you may have heard of, are pieces of asteroids that collide with Earth and provide clues to their parent asteroids. Unfortunately, for most of them, we don't know which asteroid they came from. So our scientific understanding is quite hampered in that regard. So what about that name? Well, we'll review since these are important objectives. The mission's name is an acronym that describes all of the objectives of the mission. Origins is for understanding the origin of the solar system and organic materials important to the origins of life. Spectral interpretation refers to the spectrometers on board that provide compositional information. Resource identification includes looking for commercially important materials and water that is needed for both humans and mining activities. Incidentally, water is considered a very important commodity throughout the solar system. Security refers to investigating how asteroids in the main asteroid belt migrate into the inner solar system to become near-Earth asteroids. And lastly, but most importantly, is Regolith Explorer. Our objective is to return 60 grams or about 2 ounces of asteroid Bennu from the regolith. Regolith is just our scientific term for dirt on an airless body like the moon or an asteroid, but very special dirt. I need to point out that even though we have meteorites in the Earth's laboratories, we are collecting a pristine sample of the early solar system that has not been heated by passage through the atmosphere or corroded by Earth's water and oxygen. So what about Bennu's name? Bennu was originally known as 101955 1999 RQ36. It doesn't roll off the tongue too easily, does it? Thankfully, we obtained permission to hold a naming contest for high school students. And 9-year-old Mike Puzio suggested the name Bennu, a beautiful bird that was associated with the Egyptian god Osiris. So it was perfect. So where exactly is Bennu located? Most asteroids are in the main asteroid belt between Mars and Jupiter, to the outside of my screen, essentially. Bennu orbits the Sun in an orbit that is entirely inside the orbit of Mars. So that partly qualifies it to be a near-Earth asteroid. In addition, we've realized that its orbit crosses the Earth's orbit in two places, and thankfully not when the Earth was there so far. And so Bennu's size and orbit qualifies it to be what is known as a potentially hazardous asteroid. Now, that's an astronomical term, not necessarily a qualitative term, so don't lose sleep over it, but it does make Bennu special in that we want to understand how main belt asteroids, some of them, tend to migrate inwards towards the Sun and inner solar system to be hazards to Earth. I need to also point out, we have telescopes scanning the skies every night for near-Earth asteroids that might collide with Earth. So they will give us an early warning. All right. So when we were preparing our mission, there were only 500,000 asteroids known. There are almost double that number now. They were always there. It's just our ability to discover them has greatly improved, and we are discovering smaller and smaller objects, essentially the size of a couch. It's pretty amazing. So if we could only go to just one out of these 500,000 asteroids, how in the world did we choose just one? It's like eating that proverbial potato chip. You can only have one. We needed one that was nearby so that we could reach it in a reasonable amount of time with a reasonable amount of fuel and energy, and one whose orbit was easy to get to and to return from. So that cut out most of the asteroids, dropped us down to the near-Earth asteroids, and then 192 with optimal orbits for sample return. Then we wanted one that was greater than 200 meters across, and that's because astronomers have learned that asteroids smaller than 200 meters rotate so fast they can't hold on to their loose material. As you could see from the videos, and I'll show you shortly, we need loose material to collect. So Bennu, it turns out, as you can see on the right, is about 500 meters across. It's perfect. It's about a third of a mile across, and so it was just right. In addition, we wanted an asteroid that has carbon-bearing materials in it. We didn't want to go to one that might be made out of metal. That wouldn't answer the kinds of questions that we hope to answer. So there were 5 that were probably carbon-rich asteroids, and in the end there were 2, and Bennu came out on top because we discovered there was radar information from the world's biggest radio telescope in Puerto Rico that showed its shape, that indicated there probably was loose material on the surface. So that's how we ended up with Bennu. The other thing I'd like to point out in the Bennu facts panel there is that this was all information that we knew before we even built our spacecraft. It was pretty amazing from astronomical data. Its rotation period, or its day, is about 4.3 hours long. Wow. I'm usually wishing for longer days or more days, but here we have 4.3 hours. So the rocks heat up and cool off very quickly. Okay, so here we go. In the lower left, you see a star field with Bennu circled. That is one of the best pictures of asteroid Bennu we will ever get from the Earth. Most telescopes can't see that faint, and so that's the best we can do. Thankfully, however, the radio telescope at Arecibo was able to ping the asteroid, and as it rotated, it built up data that they converted into a shape model. And over on the right, you can see rotating Bennu as we approached it in 2018, and that we did indeed determine the shape perfectly. We even were able to see that large boulder on the edge. By exploring a known asteroid and bringing back samples to analyze in detail, we'll be able to calibrate astronomical measurements and refine theories to greatly advance our scientific understanding. One theory that was already refined is that we were expecting rocks about 4 inches across or 10 centimeters across throughout the surface. Unfortunately, when we arrived, we found many, many huge boulders. So that presented our first big challenge. I'm happy to say we were able to rise to the challenge. Okay. So here are some examples of carbonaceous meteorites in the laboratories that are the closest types to what we expect at Bennu. So when you look at the pictures, imagine Bennu is actually black. Our cameras were optimized to be able to image very, very dark objects. Only 4% of the light that strikes Bennu is reflected back to Earth so that we can see it. All right. The sample collector will contact the surface for only 5 seconds, as shown here, much slower than this. The spacecraft will slowly approach the surface, and once it makes contact, it will blow that gas, a nitrogen gas. Once we've verified that we've collected some sample, we'll stow it into the sample return capsule. Stow the arm, close the capsule lid. As the spacecraft travels back towards Earth, it will eject that capsule again. So let's look at the TAG-SAM, touch and go sample acquisition mechanism, in a little more detail. Lockheed Martin tested this device in an aircraft known as the Vomit Comet. At the top of the curve of the path, it provides a weightless environment for about 20 seconds. All we needed was 5. So we did indeed prove that this technique will work. You saw that the rocks were stirred up. They're trapped inside that cylinder. So we needed to show that this technique would work in a low gravity environment. On the left, we have a cartoon that shows how the gas flows through the tubes, stirs up or fluidizes the rocks. The gas flows out the mesh, but the rocks become trapped inside. We'll even be able to look at that mesh for fine-grained particles as well.
Hi, Dolores. It's Jeff.
Yes.
Sorry. So this airplane that they tested this on, is that the same one the astronauts fly on?
Yes, absolutely. I'm sorry. The Vomit Comet is the one that astronauts train in and try to conduct tasks to feel what it's like to be weightless. And so they may make these loops 50 times, 100 times. And so some astronauts, have a little bit of trouble with that sort of trajectory.
Okay.
Thankfully, our robotic instrument didn't care, and we were able to do many, many tests. So that's why it's called the Vomit Comet.
Thank you so much.
Thank you. All right, but what if we don't have 2 centimeter or 1 inch sized particles and we happen to touch on something larger, as you see here? Well, many, many tests were done to ascertain whether we could still collect enough sample. So here you see a pretty big blast, large rocks that prevented complete contact with the surface. And I'm happy to say that this test, along with many, many others, was quite successful. Indeed, even though we have a 60-gram baseline or 2 ounce desired sample, That's about the size of a Snickers bar. Our collector can actually collect up to 2,000 grams. So I am really looking forward to a huge sample. Then in 2023, you can mark your calendars. We'll arrive past, the spacecraft will fly past Earth and eject the sample return capsule. The capsule itself will heat up, but it will take all of the heat of reentry, protecting our sample. The parachute will deploy and the sample will arrive a little bit slower than it would normally, and we'll be there to retrieve it at the Utah Test and Training Range just west of Salt Lake City. It will immediately be taken to Johnson Space Center, where they are building a special clean room for it right now as we speak. So here's an example of some of the laboratories that are currently calibrating, testing, practicing, analyzing additional meteorites in anticipation of the Bennu samples. And there's probably five times this many that would like to analyze the sample. Over in the lower right-hand corner is our friend from Johnson Space Center, curator Kevin Ryder, who's going to curate our sample. That cabinet contains the first samples of materials that we used in creation of the spacecraft. All right, so this is what we encountered as we approached asteroid Bennu. It's beautiful, it's interesting, but oh dear, it has many, many rocks. So that was our first challenge. So what have we discovered so far after studying asteroid Bennu for several years? Well, right off the bat, we discovered lots of boulders up to almost 200 feet across. Rock slides, ridges, thermal fractures, a lot of rock movement on the surface that has been interesting. And we have confirmed that asteroid Bennu is what we call a rubble pile asteroid. It is actually made up of larger chunks of asteroid bodies underneath, and it has a lot of cracks and pores that are quite intriguing. So we think that Bennu broke apart from its parent asteroid and then reassembled from some of those pieces. We did discover water in the rocks. Wow, that was a huge discovery. Our spectrometers were able to discern this water, and that is a useful discovery for all kinds of purposes. Many of the minerals were transformed by water, and so many of them are phyllosilicates or clay minerals, and we think that there's magnetite there as well. And we confirmed that Bennu is a close match to some of the meteorites we have in our laboratories, but there's some important differences as well. So it's a very intriguing object. We also learned and confirmed that the sun's radiation on Bennu's black surface caused its day to speed up by 1 second per year, and we actually measured that. We also determined that its position in its orbit gets closer to the sun by 131 feet per day. So where we predict it should be in its orbit, it changes a little bit because the sun's radiation strikes the hot surface, and when Bennu rotates around to the darkness of space, it re-irradiates that energy back out and causes its rotation and its orbit to change just a little bit. But over millions and millions of years, we think that has caused asteroid Bennu to move from the asteroid belt closer in towards the Earth. So it's a very important asteroid.
Hey, Dolores, we had a
Yes.
question.
Okay.
Why is water so important?
Why is water so important? Well, if we send people out to explore planets or asteroids, we can't bring enough water for us to survive. So if there's water already in the rocks, we might be able to heat them up a little bit and extract that water. In addition, mining activities will need water to cool their equipment. And so they too can use the water that's already there. So, great question. So that brings me to one of the most exciting discoveries of our mission, and that is never before seen particle ejections from the surface of an asteroid. We've never seen anything like this on any other solar system object, and it was discovered completely by accident. So here they are. I don't know if you can see my pointer. On the left is asteroid Bennu. It's a composite picture because in order to see the particles, you'd have to look at a very, very long exposure, which actually is not even 20 seconds. And asteroid Bennu would be blasting the picture. So we made two pictures, one that shows Bennu clearly, one that shows the particles clearly. These were discovered by accident. And so I want to encourage all of the students here today to always be observant, always explore, always be curious. You just never know what you're going to find. The astronomer that discovered these was actually, for fun, trying to see if he could identify the constellations in the background. He found this star cluster that he couldn't identify, and it turned out to be these very, very important particles. So let me show you what they're actually doing. For some reason, these particles are being ejected from a spot on the surface of Bennu. Some of them fall back to the surface right away, as you can see. Some orbit the asteroid for a little while and then fall back, and some are ejected completely away. We can't predict where these events will occur. We just are able to catch them because we happen to have particular observing orientations. By tracking these particles in many, many pictures that were taken, we were able to greatly refine the gravitational field of asteroid Bennu and improve our spacecraft's operations. All right.
Dolores, that's so cool. So
It's
the
very
campus had
cool.
it is really neat to see something like that, that rocks are flying off of an asteroid. And you guys saw it in the picture.
Yes.
How big are those rocks?
So the rocks range in size from maybe a few centimeters to maybe a few are as much as 10 centimeters, but most are pretty small. And we don't know exactly what is causing them. It could be from micrometeoroids striking the surface of asteroid Bennu and causing particles to be ejected because there's such a low gravity field. Or there could be rocks that are breaking apart and ejecting particles as well.
So now the campers had another question, or had a question for you. So how hot or cold is the surface of Bennu?
So the surface ranges from the cold of space all the way up to barely 200 degrees Fahrenheit. So not quite hot enough to boil water. But this action of hot and cold over a few hours' time causes the rocks to break apart pretty quickly.
Thank you.
I should also mention the gravity field, that Bennu is the smallest object anyone has ever attempted to fly by or orbit. And so that was a great milestone for technology. In addition, we set the Guinness World Record for closest orbit ever achieved. And then we broke our own record as well. So that was kind of a fun thing that we didn't plan for, but we knew would occur. So what do we see when we look at Bennu? Well, the first thing we see are some craters. And over here on the right in the square, you see a very large kind of rugged crater. It's a little bit larger than a football field, and it is actually considered large enough to possibly have broken apart asteroid Bennu, but for some reason it didn't. And so our astronomers have learned a lot about the internal strength of asteroid Bennu by looking at that crater as well. Here's an image that gave us some heartburn here. There are regions that contain very, very large boulders. Even the smallest ones in the image are too large for our 15-inch collector. For instance, the one in the middle is the size of a dump truck. So we could touch down on top of it or next to it, but it would be a very hazardous region. So there are rocks on top of rocks, rocks that have obviously wiggled around and moved in between larger boulders. And so this has told us a lot about the history of Bennu in the last few million years. We're also interested in the white rocks in the picture. Over on the left, you see some that are sort of light gray with white spots. And so that's telling us there's material of different compositions here that we're very interested in. Here's another region that has huge boulders. Here you can see that the smooth boulder on the left is 40 feet across. That is huge. Some boulders are smooth, some are lumpy. We call them a cauliflower type of boulder. This would certainly be a terrible place for our sample collector. The red circle is the original target area that we needed to be clear, flat, smooth, without any drastic slopes. It turns out there are no such places on asteroid Bennu. Thankfully, our flight dynamics teams are so fantastic that they were able to determine that they could set the spacecraft near an area that was 5 meters in radius or 10 meters across. That was still a bit of a challenge, but we were able to come up with quite a few sites that would have been adequate. We came up with a list of 16 sites, then a Sweet 16, an Elite 8, and then a Final 4 that we investigated in more detail and ended up with our primary site and our backup site. So how did we select these sites? Well, 4 criteria: safety of the spacecraft, sampleability, which means having the right mixture of small rocks and particles that we desire, deliverability, the ability to deliver the spacecraft to the right spot, and to be able to deliver material into the tag-SAM head properly. Lastly is science value. Safety comes first because nothing else matters. If we happen to scrape a boulder on the way in or out, we would be in deep trouble. So the science value necessarily came last. It turns out, however, that we would be happy with every sample that would be returned. The science team constructed a variety of global maps like the ones you see here. Our instruments all start with an O for OSIRIS. OVIRS is the OSIRIS-REx Visual Infrared Spectrometer, and OTIS is the OSIRIS-REx Thermal Emission Spectrometer. The one on the left gave information about composition, and the one on the right gives information about the heat. And these were used to construct a variety of global maps of composition, heat, rock sizes, fractures. And the science team carefully evaluated and scored every site. In the upper right is a collection of hundreds and hundreds of measurements of boulders. So we had volunteers as well as team members who marked the longest dimensions of every rock and boulder that they saw in the image. And we were able to come up with boulder maps and hazard maps. So all of this information was combined to help determine the best sites. So in the end, we ended up with 2 sites that are named after birds in keeping with the Bennu theme. Bennu was a heron, so we figured places on asteroid Bennu should be named after birds as well. This is an informal name, not an official name, but we call it the Nightingale site. And you see it on the lower left that it's located near the pole of asteroid Bennu. And on the right picture, we have a beautiful picture of a crater with boulders surrounding it and a cartoon of the spacecraft for scale. So that's how it looks as we approach. These sites were chosen also for their probability of containing organic materials and fine-grained material as well. This is the Osprey site. It's located near the equator of asteroid Bennu. It looks a little bit smoother, but on the other hand, those rocks that we can see in the picture are actually too large to be collected by our collector. There are some regions there that are suitable, thankfully. So to give you a little close-up view of some of these rocks, here's a view of a boulder that is 5 meters or 15 feet across on top of a larger boulder. So the light colored one on top is about 15 feet across. And you can see lots of cracks because it's been fractured. And in the lower left of the cauliflower rock, you see a rock that's gray with some white modeling in it. And to me, as a meteorite person, that's very intriguing. We've never seen any meteorite that looks like that. So it's very exciting. Here's a picture of a large boulder, 45 feet across. So this is, as big as some houses that split apart. And notice in one of the cracks on the one on the right that you can actually see very fine particles that have settled down into that crevice. Some of this is due to movement of rocks on the surface of Bennu from collisions between asteroids and material gets thrown around. All right. This looks a little bit better, I think. But even so, there's some big rocks in that area. But I wanted to show you something encouraging. So recently, in April, we had what was called our checkpoint rehearsal. This rehearsal was a very important milestone to help us understand how to approach the surface very, very slowly and to be able to use our navigation system and our natural feature tracking system. So I'm going to redo this. This actually took place over a 10-minute time period. It was excruciating, but that's okay. We want to be better safe than sorry. And as we were coming down, we wanted to compare the rocks and boulders that were seen by the spacecraft with the atlas that we had uploaded. And if the spacecraft sees anything different, it will stop and wave off its maneuver and back to a safe place so that we can regroup. The important thing is to remember we will be 15 minutes away from asteroid Bennu. That is, the Earth will be 15 minutes away for communications. So a lot of our collection procedure has to be semi-autonomous. Once we press that button, the spacecraft will be able to do some maneuvering, but not a lot. And we won't have any verification of the procedure for 15 minutes. All right. So with that, let's fly over the Nightingale site so you can see the difference between two-dimensional pictures and three-dimensional reconstructions. This animation was put together by many images and what we call a digital terrain model. We had a laser altimeter on board that was able to measure the distances to every rock. And so these flyovers were constructed to help us understand how to get the spacecraft into the site safely. Outside the crater, you can see there are many large boulders, so we want to be as precise as possible. Next is the Osprey site. So here we go. It looks good in the two-dimensional view, but now we come a little bit closer at an oblique angle, zoom all around the crater. It's fairly flat, but not completely flat. The science team is particularly interested in that dark, smudgy area in the center. We don't know for sure if that's fine-grained material, perhaps full of organic materials, or it could be a boulder, a darker boulder peeking through the bottom of the crater. So that's the challenge. We need to get into the site safely and to get out again. And we will be as careful as possible. If for any reason we need to wave off a collection maneuver, we will do that. All right, so what is next for the OSIRIS-REx spacecraft? Here you see the match point rehearsal that will occur very shortly, August 11th. It will take the spacecraft closer than it's ever been to asteroid Bennu. It will only be 131 feet away from the asteroid. So some of you may recall that the Apollo missions sent astronauts very close to the moon. First, they swung around the moon, then they orbited the moon, but didn't land. It was only when the engineers were absolutely sure it would be safe that they actually attempted a landing. So we're doing the same thing. We're practicing the checkpoint and match point rehearsals to make sure that we understand the terrain, the gravity field, the way the spacecraft will maneuver at every point. Our first tag opportunity to collect our sample is October 20th. We call that our first opportunity because we actually have a long window of opportunity of several months. So if for any reason we wave off that particular collection, that's okay. We have plenty of time to regroup and decide the next step. So I'm happy to say that the best of Bennu is yet to come, especially when we return the sample to the Earth's laboratories. I thank you so much for inviting me to speak with you today. And for those who want more information, check out our website at asteroidmission.org. And you can tune in to the Lunar and Planetary Labs Summer Science Saturday, this Saturday, August 1st at 1 p.m. Dr. Dante Loretta, our principal investigator, will be giving a talk. And I'm sure he will have a little bit different perspective than I have on the mission. So there will be some review, but I'm sure you'll learn some new things as well. Register free at the Zoom link. And thank you again for your attention, and I'd be happy to answer any questions you might have. Thank you.
Sorry, I had some technical difficulties getting.
That's okay.
So that was an awesome presentation, and we had a few questions build up, and so I wanted to try
Great.
to get them out to you here. So
Okay.
one of the questions was, what causes some of the rocks to be so smooth if there's no water or wind on the asteroid to make them smooth?
That's an excellent question. We don't know for sure. It's possible that it has something to do with the way the rocks fracture. For those who are familiar with geology, you might recall that there are certain minerals and rocks on the earth. When they break in cleavage planes. That might be what's going on Bennu, but only some are flat. Some are quite lumpy. Some are breccias or rocks, different rocks held together by some sort of matrix in between. And so there's a great variety of different rock types on asteroid Bennu. And I hope we collect a little bit of each one. It'll be very exciting to try to untangle the history.
Great. So a few more here.
Okay.
So you have 2 sites that you can collect samples from.
Yes.
If you go down and you try to collect a sample and there's a problem, are you going to have another opportunity to try again?
Yes.
Okay.
Yes. So I neglected to mention that we have 3 tanks of nitrogen gas on board. So we have the ability to make 3 collection attempts. Now, whether we go back to the same site, to the Nightingale site, the primary site, or go over to Osprey is yet to be determined. It all depends on the circumstances. But we actually have 3 possible attempts.
Great. And then so you'd mentioned, I think on the second site, Osprey, that dark area that might be organic material. What organic material are you? That was a question we had that you might expect there.
It's possible there's some carbonate materials, clay materials, and essentially organic just means anything with carbon, hydrogen, and oxygen.
Okay.
Nothing living, just rocks with those components in them. Our organics team will be looking for all kinds of organic materials, amino acids, precursors to amino acids that have been found in meteorites, carbonaceous meteorites. There are lots of questions about those, and we hope Bennu will help answer some of those, especially because we are bringing back a clean, protected sample. The meteorites that we have in our laboratories have all been exposed to Earth's air, water, fingerprints, people breathing on them, and so they are necessarily contaminated by the Earth. Ours will not be.
That's awesome. So just, I think 2 more questions here, and then we'll let you go for the day. What's the biggest rock size that the TAG SAM can actually collect?
Oh, early on, I seem to recall a 6 centimeter number. We'd rather not, but we could. And there are certain orientations where 4 centimeter rocks could line up and not allow us to collect something.
Okay.
So that's why we were so careful about trying to choose a region of fine-grained material.
Okay. Now OSIRIS-REx runs off of solar power. Is there any other power sources besides solar power?
Absolutely. We have beautiful solar panels in all the pictures, but we use hydrazine as well.
Okay, that's for the rocket or the propulsion system, I should say.
Right.
Okay.
Hydrazine, and then also reaction wheels, I should say.
Okay.
And when they do that rotation maneuver to determine the mass of the sample, the engineering team has to estimate ahead of time how much fuel is in the spacecraft and how much it weighs. before and after they do that maneuver. So it's a pretty complicated mission.
Great. Oh, it's definitely complicated. It's just amazing that they can even dream these things up and then make them reality. So Dolores, I wanted to thank you so much for educating us on the OSIRIS-REx mission and Asteroid Bennu. We also want to thank our partner, the Science Vortex, and all the viewers who tuned in today. We really appreciate that. Make sure to follow Verde Valley Stream Council on Facebook to be notified of future science cafes. I will say some of our viewers were really interested in the slides that you had, and certainly in the URLs for the event that you have coming up this Saturday. I will try to get that from Dolores and post it on our Facebook feed. So again, if you're using Facebook, search for VV Stream. I will also try to send that out to the people who registered through Eventbrite as an email, as a follow-up email, so that you have that information as well. So, and if you have any problems, you can send me an email. I believe, through the Eventbrite feed there, or emails that you got, you should be able to respond to me, and I'll try to do any follow-up questions you might have for there. So,
and I'd be happy to answer any questions people have, as they mull things over in their minds. I'd be happy to answer any other ones.
Great. So,
by email or whatever.
So for Dolores Hill and the great team down at the Lunar Planetary Laboratory, I'm Jeff Anderson. Everybody stay safe and have a wonderful rest of your week. Bye.
Thank you.